Hello everyone, my name is Pibin Abram and in today's video we are going to talk about electric flux, which is represented by a symbol phi. So let's get started. So as the name suggests, electric flux. The first thing that we have to understand, this word flux is important. Now what is the meaning of flux? Flux literally mean to flow. Let me write it. Flux literally mean to flow. Now if in front of this word, if I add water, then I can say water flux, right? So water flux means the flowing of water, right? And if I add air in front of it, I can say air flux. Air flux means the air which is flowing, right? Okay, so our topic is electric flux, right? Electric means we're talking about electrons. Electrons means we're talking about charge means there must be an electric field. Electric field means there must be electric field lines, right? So basically electric flux actually mean electric field line which are actually flowing through any particular surface, right? So that is something which we are going to find out in today's video. So let's move forward, right? Okay, so what actually is electric flux, right? So if somebody defines it, right, so it is defined as surface integral of electric field over a surface, or mathematically it is given as by this relation phi is equals to E dot dA, right? By looking at this definition, well, I can't understand much, right? It is defined as surface integral. What? Like I'm not able to understand this, right? So let's try to actually feel it, right? Let's try to understand it in deep sense, right? So surface integral, okay, don't worry, we'll get to know it, right? In simple words, I can also say this: it gives us the total number of electric field lines passing through a surface normally, right? Now this is important. It gives us total number of electric field lines which are passing through a surface normally, right? So you guys have to remember this definition, because we are going to use the definition in the later of this video. So this definition is important. I'll just repeat it again. It gives us total number of electric field lines, right, which are passing through a surface. It can be any surface. It can be a rectangle, it can be a circle, right? It can be a 3D surface, it can be a 2D surface, right? Whichever surface you want to imagine it. So total number of electric field lines which are passing through a surface normally or perpendicularly is what is called your electric field line, right? Okay, so I'm going to put this thing at hold, right? So before we understand this properly, we have to understand one more term, which is your area vector. Area vector is something which we have to understand. Yes, you heard it right, area vector, right? Now some of you might be wondering, how come area become a vector, right? Okay, don't worry, let's try to understand this and then we'll move forward, right? Okay, so one of the simplest example to this is a rectangle, right? Let me draw a rectangle, right? Let's say this is my rectangle. Okay, great. So this is my rectangle, right? Okay, now let's say this is along x-axis, this is along my y-axis, right? And let's say it had a magnitude of a, the length is a, and the breadth is b, right? And very nicely, if somebody asks you what is the area of this rectangle, I will simply write a multiplied by b, right? A cross b, or length into breadth, right? Yes or no, right? Okay, so how I can say it's to be area vector? So you have to imagine with me, right? You have to visualize this. Okay, let's imagine this length to be my a vector. It's actually a vector quantity. Let's imagine that it's actually a vector, right? I can visualize this length to be a vector, that is a vector, and I can visualize the breadth to be b vector, right? Now if I say that area is a vector, let me write it here, area vector, right? That is simply given as a vector cross b vector, right? And we have studied now vector that a cross b can also be written as a b sine theta. Yes or no? Where theta is the angle between a vector and b vector, right? And very nicely I can see it here that my a vector and b vector, they are actually perpendicular. They are making an angle of 90 degree with each other, right? That means I can write it here a b sine of 90 degree, right? And we all know sine 90 is actually 1, right? And that's how I can say your area vector, which I can write it A vector, right, is simply given as AB, right? So actually your area is a vector quantity, right? I hope you guys can understand this, right? Okay, as I said, it's a vector quantity. It must be having a direction, right? Now what is the direction, right? Now that is important, right? Now we have studied in our vectors chapter, that is in our 11th standard, we have studied, right? And I'm sure for all those people who are, you know, having maths, they must be knowing this. So if I have a vector, if I have a vector A vector and I have vector B vector, and if I do a cross product of those vector, right, then the resultant vector is always perpendicular to the plane containing A and B vector, right? That means it will always be perpendicular to the plane containing A and B vector, right? That means, for example, if this is my A vector and this is my B vector, right? Let's say this blue pen is my A vector, this white pen is my B vector. Then if I do A cross B, right, A cross B, then the resultant vector will be along my index finger. Yes or no? The resultant vector will be along my index finger, right? It is perpendicular to my white pen, it is perpendicular to my blue pen, it is perpendicular to A, it is perpendicular to the B, right? So basically the direction of A cross B is always perpendicular to the plane containing both A and B whenever we are doing A cross B, right? So I hope that is understandable, right? So in this particular case, right, in the case of rectangle, right, when I do A cross B, right, so can you guys see it is along the Z axis, right? It is actually coming out of my board. A cross B is actually, see, A, you guys can find out the value of A cross B by right hand thumb rule, right? From A to B, when I move, right, my thumb is actually give me a direction of resultant vector, right? So from A to B, the thumb is pointing it outward, right? It is pointing outward of the plane. I hope that is understandable, right? Okay, great. So the direction of area vector AB coming out of the board, right? Sometimes you can write it B cross A, right? B cross A will give you the answer. So at that particular, for B cross A, the area vector will be going inside the board, inside the whiteboard, right? I hope that is understandable. Is that understandable? So basically what we learned, that your area is a vector quantity, right? Okay, very important. Okay, this was a 2D figure, right? Important, this is important, you have to understand. This was a 2D figure. So whenever we talk about 2D figure, right, the area vector will be perpendicular to the surface, right? So it can be perpendicular, it can come outward, or it will go inside also. So both the direction is possible because both the directions are perpendicular to the plane, right? I hope that is understandable. For 2D figures, right, 2D figures in physics, we call them open figures, right? We call them open surfaces, open figures, it's up to you, right? Surfaces, right? We call them open surfaces, right? So for 2D figures we call them open surfaces. For 3D figures, let's talk about 3D figures, right? 3D figures are known as your closed surfaces. All right, your 3D figures are known as your closed surface. For example, let's take an example of cylinder, right? Cylinder. Let's take an example of cylinder. Let's say I have a cylinder, right? Let's say I have a cylinder. All right, let's make a good cylinder. Alright, so this is my cylinder, you guys can see this is my cylinder, right? So I guess I can always, so there are two circles here, right? So whenever we talk about closed figures, right, the area vector will always, again for this also, area vector will be perpendicular to the surface, but the difference is it will always be perpendicularly outward. It will not, see, for example, this circle can have area vector in the upward direction and it can go downward direction. So we will neglect the downward direction. We will always consider direction which is going outward, right? So area vector outward will be the direction, right? For example, for this surface, area vector can be this, or it can go inward also, but we will not consider the inward direction in the case of 3D figures, in the case of closed figures, right? So we will always take area vector to be going perpendicularly outward, right? Very similarly for this case, this is the right one, inside one is the wrong one. Very similarly for this surface, area vector is going perpendicularly out, perpendicularly in is not applicable. We will not consider that, right? So I hope that is understandable. So this was some basic which we must all know before we understand electric flux. I hope that is understandable. If that is understandable, let's move on with our electric flux, right? Okay, great. So till now we know what is electric flux, right? Let's remember the definition, right? Definition was, it gives us total number of electric field lines passing through a surface normally, right? Okay, great. Now remember that formula with you, right? Let's say I have a surface. Alright, so I have this surface, right? So let me just take this as, I'll just copy this. Okay, now I have this surface, right? And let's say the electric field lines are going through this surface, right? Let's say I have electric field line which are going like this. Okay, all right. So you guys remember the definition that we studied, right? The definition was, it gives us the total number of electric field lines which passes through a surface perpendicularly, right? So can you guys see, this is actually perpendicular to the surface, right? These three electric field lines, right? So basically I can write, for this diagram, my electric field line is actually 3, because 3 electric field lines are passing through my circular surface. Is that yes or no, right? Is that a yes or no? Yes, great, right? Okay, so let's take one more example. All right, so let's say, yes, I have the surface, right? Okay, great. So let's make the electric field line. Now I had the same surface this time, right? I had the same surface and I can see these are perpendicular, same surface I had. The only difference this time is that my number of electric field lines are increased, right? Number of electric field lines are increased. Now this time I have 5. I can see 1 2 3 4 5, right? So number of electric field lines has been increased, right? And so does your flux, right? So from these two observations I can deduce one thing, that your flux depends upon the intensity of your electric field, right? So in the first case, as you can see, the intensity of electric field lines were less, right? There were distance between one field line to other field line. At the same time, when I look at the second diagram, I can see more number of electric field lines were passing, right? Because distance between them is less, that means the intensity is more, right? So more the intensity, more the electric flux. Yes or no? I hope that is understandable, right? Okay, great. So flux depends upon electric field intensity, right? So I can say that is my equation number 1, right? Now one more important observation that you have to observe here, that my area vector for this surface is obviously perpendicularly out, right? It's a 2D figure. It can go perpendicularly backward also, but let's assume it is going perpendicularly in the same direction of that of electric field, right? So area vector, electric field are having an angle of 0 degree, right? So the angle made by area vector and electric field in this particular scenario is 0, right? And for the second figure also, angle made by area vector and the electric field is again 0, right? Keep that observation in your mind, right? So this was your first case, right, in which we were able to, you will able to see that your flux depends upon the intensity of electric field lines, right? Great. Let's move on to the next case, right? Okay, so again I have the surface, right? So let's say this time I will make the equal number of electric field lines, right? So let's say I have 1 2 3 and 4. I have you guys can see, let's say one more, I can make one more, right? Let me make one more, right? So I have 1 2 3 4 5 electric field lines are there, right? And the same structure, right? So I can say my phi for this particular case is actually, see, I can consider this one also because it's actually passing through it, right? So I'll consider this one 1 2 2 3 4, right? So I have phi to be 4, right? Okay, great. Same figure, right? Same figure, but this time I will make the area bigger, right? I will make the area bigger, right? So you have to understand this. I have made the area bigger, right? And same number of electric field lines I will pass, right? That is 1, that is 2, this is 3, right? I'm very particular that I make the same number of electric field lines, right? Because I have to prove a point to you guys that, okay, so in this particular case the area was bigger. As you guys can see, the area was bigger, right? So as the area is bigger, 1 2 3 4 5, right? All the 5 electric field lines are passing through my surface, and in all the example they are 90 degree, they are perpendicular to the surface. Yes or no? They are perpendicular to the surface. I hope you guys can see that, right? So your flux in the second case is 5, flux in the first case is 4, right? In the first case the area was smaller as compared to the area in the second case. Now what does this tell us? Again, you guys can easily deduce that the flux again depends upon the area of the surface that you're choosing, right? If the area is more, like we guys can see in the second case, right, then more and more number of electric field lines can pass through the surface perpendicularly, right? Now in the first case the area was less, right? So although there were electric field lines, but as the area is less, the less number of electric field lines will pass through that area perpendicularly, right? So I hope that is understandable. So that means I can deduce that my flux also depends upon the area of the figure or the surface that I am choosing, right? I hope that is understandable, right? Again, one more observation that you guys have to see over here, that the area vector was again A and electric field line was again in that direction only, right? So again the angle between area vector and electric field line is 0 in this situation also, right? And same thing is happening, area vector is perpendicular, right? And the angle between area vector and E vector is actually 0. I hope you guys can see that observation, right? Okay, now so we have to be careful, right? So two observations we are able to understand here, right? First one was that your flux depends upon the intensity of your electric field. Second, the flux depends upon the area of the surface that we are choosing, right? In both the cases we saw that the area vector was making an angle of 0 degree with the electric field, right? Now what will happen if it makes an angle, if it was obliquely with the electric field, if the area vector was obliquely with the electric field lines, right? So let's see what is going to happen, right? And also you have to remember the definition says it gives us the total number of electric field lines that are passing through a surface normally or perpendicularly, right? Okay, so again let's make the same figure, right? Okay, right, so I have the same figure with me right now. This is an exercise, right? So same figure, right? So I can say here this is my area vector, which is obviously perpendicular to the surface, right? Great. Now this time my electric field lines will be making an angle with the area vector, right? So let's say my electric field lines are passing like this. All right, let me make it nicely, right? So this is my electric field line, right? This is how the electric field lines are going. Okay, this is not parallel, let's say they are Yeah, so this is how the electric field lines are going. Yes, so I hope you guys can see that this is my electric field. Right now I can see very nicely here that my electric field line is actually making an angle of theta degree with the area vector. I hope you guys can see that, yes or no, right? It is making an angle of theta degree with my area vector, right? So I can also, I can see that the electric field has two components here, right? One component is E sine theta, which is like along the surface going downward direction, and one component is your E cos theta. Now this E cos theta is the perpendicular component. Can you guys see that? E cos theta is the perpendicular component for the electric field, right? Now this gives us an important revelation, right? Now what is that revelation? That actually it depends upon the angle also. It actually depends upon the angle also, the angle between the area vector and the electric field lines, right? So your flux depends upon the angle also, right? Angle also, it depends upon the cos of theta, right? So from our two observation, okay, let me just put this observation at hold, right? Let me put this observation at hold. Let's talk about the two observation that we were able to understand. That is, first one was the flux depends upon electric field, right? The second observation was the flux depends upon area, right? From these two observation I can formulate, I can say very nicely, you have to see that flux depends upon electric field as well as area, right? I can say flux can be also given as E times of A, multiplication of electric field multiplied by the area vector, right? So if I go with this, right, let's look at here, right? Let's look at here. Can I write it? Phi is equals to, okay, always remember this electric field lines, they are perpendicular field lines, right? Perpendicular to the surface, right? So keeping that in mind, can I write here phi is equals to electric field which is perpendicular to the surface, right? Electric field which is perpendicular to the surface, right? Now which electric field is perpendicular? E cos theta is the perpendicular to the surface, yes or no? I hope that is understandable, right? Multiplied by the area vector. So can I write phi is equals to E A cos of theta? Is that a yes or no, right? I hope you guys can understand that. Yes, right? So keeping that in mind, I can say that phi can be written as E A cos theta, and we know, we have studied, right, that if I have a vector that is given as AB cos theta, then I can also write it as A dot B vector, right? This is something which we have studied in our vector classes, right? So can I write phi is equals to E vector dot A vector, right? Is that a yes or no, right? I hope you guys can understand that. Phi, that is my electric flux, and E is your electric field lines, right? Electric field lines. See, basically electric field lines or electric field, right? We are talking about the same thing, right? And A is the area vector, right? Again, phi is a scalar quantity, right? Phi actually gives you a number. Electric flux is actually a number. That means how many electric field lines they are passing through a surface normally. It's actually a scalar quantity, it's not a vector quantity. It is not going to have direction. We'll never say that electric field is in that direction or this direction. That is not something which we have to do, because it's a scalar quantity, right? I hope that is understandable, right? Okay, great. So if that is understandable, let's do a very simple problem so that you guys can get a hang of it, right? Okay, one more thing before we do the problem. Okay, what is the unit of electric flux, right? What is the unit of electric flux? So I can write flux to be electric field multiplied by the area vector, right? So we know area means the unit of meter square, right? Yes, electric field will be having a unit of Newton per coulomb, right? Yes or no? Electric field will be having a unit of Newton per coulomb, and area will be having a unit of meter square, right? So the flux will be having a unit of Newton per coulomb meter square, right? I hope that is understandable, right? Is that a yes or no? So let's do a small question so that you guys can understand, right? Okay, the question is that electric field that is passing through a surface perpendicularly is given in the form of 2 I cap plus 3 j cap Newton per coulomb, right? And the area vector that is given is actually 3 I cap plus 2 j cap meter square. Find the flux, find out the flux, find the value of phi, right? It is very simple, right? We have studied, it's very simple, we have studied phi is equals to E dot A, right? E dot A we know, right? It's actually a dot product, right? So very nicely I can write 2 I cap plus 3 j cap dot 3 I cap plus 2 j cap, right? Simple, right? So 2 and 3 I cap will, it will be I dot I is actually 1, so this will be 6 plus 3 and 2, again 6 j cap dot j cap will be 1, right? So 6 plus 6, the value is 12, right? This is Newton per coulomb meter square. I hope that is understandable, right? So basically you guys can see, although E and A are vector, you are actually getting a number, that is 12 number of electric field lines are actually passing through that surface perpendicularly, right? I hope that is clear to everyone, right? If you have any doubt, you can ask me in the comment section, right? And I hope all of you are doing good. Stay home, stay safe.